Right, so we're going to talk about triple integrals. In cylindrical coordinates.
Same general theory as polar plus z, right?
Yes. And you know what was really funny, Chris? That is exactly what your brother said when you. All right, so in cylindrical coordinates, just a reminder, when we're in cylindrical coordinates, we're in the xy plane, we are in polar coordinates. And then our z coordinate is just z. Like Chris said, polar plus z. When we talked about double integrals in polar coordinates, we approximated the area of a polar rectangle in the xy plane or in the r theta plane. We said was r sub I, r bar sub I, delta r sub I, delta theta sub I, where r sub I was the average radius in the region, in our ith rectangle. So just sketching a quick picture as a reminder, if we're in the xy plane or in r theta, we want to think about it in polar coordinates. We said we had our little radii, and we approximated the area of this little rectangle. We said this side was delta r sub I, and this side was the average radius. Delta theta sub I. So we're talking about the area of this little sector. So what we're going to do with cylindrical coordinates is take this and just basically stretch it upwards in the z direction to get an expression for our volume element for a triple integral in cylindrical coordinates. So I'm going to take this and I'm going to draw my x, y, and z axes. And we have the little polar sector in the xy plane. And here's theta equals 0, theta equals pi over 2, and this is z. So in the plane down here, we have our little sector. So that's this little sector here. And we're just going to project this upwards. And so we're going up onto the z-axis, and we're going to have a little kind of a cylindrical box is the way I kind of think of it. So there's our little cylindrical box. And the height here is, this distance is just delta z sub I. And the volume of this little box, and This is our radius projected out. The volume of this little box, delta V sub I, is just the area of the base times the height. So it's just going to be our average radius in the ith interval, delta Z sub I, that's our height, times delta R sub I, delta theta sub I. So we're just taking that little polar rectangle, stretching it up into a cylindrical box, and approximating the volume of that little box. So we're going to sum over all the blocks in our region in space to do our triple integral, and take the limit as delta V sub I gets smaller and smaller. And again, when we're saying delta V sub I is getting smaller and smaller, we're saying the largest diagonal of these little blocks is approaching 0. And so we take that limit and we sum over the entire region, and that gives us our triple integral in spherical coordinates. So so I'm skipping some steps that we've talked about before, where we're summing over all the blocks, taking the limit as delta V approaches 0, so the triple integral over our region of some function f of x, y, z dv in spherical coordinates is going to be the integral from theta 1 to theta 2, the integral from g1 of theta, g2 of theta, and the integral from h1 of r theta, h2 of r theta, f of r theta and z of r dz dr d theta. And the way I've set up the limits of integration, we've defined the triple integral and talked about how we evaluate it kind of all in one step. Theta varies from theta 1 to theta 2. R varies from g1 of theta to g2 of theta, and z varies from h1 of r theta to h2 of r theta. And a couple of things to notice about our triple integral. The outer integral is exactly like our integral in the plane, our double integral in polar coordinates. And our inner integral, we represent f in terms of r theta and z rather than x, y, and z. And our inner integral gives us the integral for the z component. So it's really not much new here. We're just switching. We're relatively familiar with polar coordinates. We're just adding the z component. And the order that I set this up for was for a radially simple region, but like any other triple integral, there are 6 possible orders of integration. We can change the order of r, dz, dr, and d theta in any combination that we want. Normally, in cylindrical coordinates, you're going to set your order up r, dz, dr, d theta. That's kind of the normal order of integration. And we use cylindrical coordinates when our region in the xy plane is easy to set up in polar coordinates. And then we just add our z coordinate to that polar area in the xy plane. really not anything really new. Just looking at a different coordinate system. So questions on our setup. So all I wanted to do today is just a couple of examples of setting up integrals in cylindrical coordinates, and then let you guys work on some. All right, so let's take a look at a couple of examples. So we want to convert this triple integral to cylindrical coordinates. So there's our triple integral. We want to convert this to cylindrical coordinates. And again, what I'm going to suggest on these when we're converting our coordinates is look at your limits and use that to sketch our region. So from the limits, from our limits of integration, our first integral is with respect to z. So x squared plus y squared is less than or equal to z, less than or equal to 4. Minus square root of 4 minus x squared is less than or equal to y. That's our next integral. And that's less than or equal to square root of 4 minus x squared. So that tells us something about a region in the xy plane, and negative 2 less than or equal to x, less than or equal to 2. So from our z limits, what kind of surface are we talking about here? X squared plus y squared equals z. That's a paraboloid. So our surface is a paraboloid, so if I sketch a quick picture, this is a paraboloid like so. And it says z varies from x squared plus y squared to 4. So our region, our surface is kind of inside this paraboloid from x squared to y squared to 4. And this tells us that minus square root of 4 minus x squared less than or equal to y, less than or equal to 4 minus x squared. So in the xy plane, what is this telling us? This is a circle, right? This is x squared plus y squared equals 4. So if I project this down onto the xy plane, the circle in the xy plane is x squared plus y squared equals 4. And negative 2 less than x, less than or equal to x, less than or equal to 2. Well, our radius of our circle is 2. So x is varying from negative 2 to 2. I just sketched the circle in the first quadrant. So now we can set up our integral in triple coordinate, or in cylindrical coordinates. So theta is going to vary from 0 to 2 pi. And it can be helpful with these. I'm going to say theta equals 0 to 2 pi.
0 to 2 pi or 0 to pi?
So this is telling us in the xy plane, this is this would be the positive square root part, and this would be the negative square root part. So we're getting the whole circle. Okay. So theta is 0 to 2 pi. R equals limits on R. 0 to 2. And z equals zero to 4? R squared to 4, where z is going between the surface and 4. So z equals, and z is x squared plus y squared, so z is going from r squared to 4. And we have x, which is our cosine theta. And then we have r dz dr d theta. So we have the integral of r squared cosine theta dz dr d theta. Not a difficult integral to evaluate, but we take a step back and be smart about it. And before we do that, anybody have a question about how we set this up? So let's take a look at this before we evaluate this. Let's take a look at this integral. So not even thinking about the limits. What is the integral of x dv, the triple integral of x dv represent? X is the distance from what thing? The yz plane. This is the distance from the yz plane times dv. So it's the distance of our little volume element from the yz plane. The x distance, what did we call that the other day? The moment about the yz plane. The yz plane is here. Our density, our mass density, we can say rho is 1 since we don't have any constant out here. So we have the moment about the yz plane of this object. The object is symmetrical. So what is that integral going to evaluate to? 0. This is the moment about the yz plane. Our object is symmetrical, so there's the same amount on one side as there is on the other side. So this integral evaluates to 0. So if you recognize that, not that I would expect people to recognize that, but if you did, you could save yourself some work. But again, not a difficult integral to evaluate, this particular integral. Questions on that one? And this kind of situation is a perfect situation for cylindrical coordinates. We have a circular region in the xy plane, and our surface is easy to transform into cylindrical coordinates. All right, let's look at one more. We want to find the volume. We have this solid inside. The sphere x squared plus y squared plus z squared equals 4. And above, the upper portion of the cone z squared equals x squared plus y squared. So that's our problem. So I always suggest that we make a sketch of what we're talking about. So I'm going to sketch the sphere in the first octant. So here's my sphere in the first octant. So there's my sphere and my cone. My cone, I'll do that one in red. So this is going to be my cone. So there's my cone, and the cone is going to cut into the sphere here. So we're talking about this volume inside this cone, but below the sphere. Right, inside the sphere and above the cone. So above the cone here and inside the sphere. So I'm going to project this intersection down onto the xy plane. And that intersection is just going to be a circle. So we need to figure out where the intersection is here. Where the intersection is here between these two surfaces to figure out our limits, our region in the xy plane. So we need to figure out where these two intersect. These two intersect where if I solve this particular, if I substitute for z squared here, I get 2z squared equals 4. So z equals 2. Sorry, z squared is 2, and z, thank you, z equals square root of 2. So if I substitute this back in here in the xy plane, I get x squared plus y squared equals 2 in the xy plane. So z squared is x squared plus y squared. So okay. So this circle in the xy plane is x squared plus y squared equals 2. So now we have everything that we need to set up our integral. So z is going to vary from the cone to the sphere. It's going to vary from the cone to the sphere. So we're inside here. So now we can set up our integral. So our volume is going to be the integral. Theta varies from what to what?
0 to power.
We could do 0 to pi over 2 and multiply by 4, or do 0 to 2 pi. R varies from 0 to square root of 2. And z varies from the cone to the sphere. On the cone, z squared equals r squared, so z equals r. And on the sphere, z squared is 4 minus x squared plus y squared. So z varies, so z is going to be 4 minus r squared. R dz dr d theta. That's, and again, like in polar coordinates, this r dz dr d theta is always going to be in our triple integral in cylindrical coordinates. So questions on the setup? Now we can evaluate this. So our first evaluation, I'll go through this one. We don't evaluate a lot of integrals in our examples, but we'll do this one. 0 to 2 pi. R varies from 0 to square root of 2, and we have, our first is just with respect to z. So we have r times z from r to square root of 4 minus r squared. Dr d theta. And this is going to be 0 to 2 pi, 0 to square root of 2, r square root of 4 minus r squared dr d theta. This integral with respect to r, we have a nice u substitution for this one, and this one is not difficult. So we get the integral from 0 to 2 pi, and we have minus 1/3 4 minus r squared to the 3/2 minus r cubed over 3, and we're evaluating that on 0 to square root of 2 d theta. And when we evaluate this, the integral from 0 to pi over 2 d theta just gives us a multiple of pi over 2. So we end up getting 8 pi over 3 times 2 minus square root of 2. So not a difficult evaluation. Questions on that one?